Okay, so we are going to go ahead and do a walkthrough of the exam one practice. The first, we're going to go pretty quickly. We're just identifying functional groups. I see I have a thiol attached to an organic molecule. Here I have a carbonyl attached to an OR group. That's an ester. I have an anhydride, right? Two carbonyls with an oxygen between. And then an amide. That's the carbonyl with the nitrogen. Now, Zyrtec, shown below, has several different functional groups. And so, let's see, what do we got? I would accept carboxylic acid. We have an ether here, an oxygen between two R groups. Both of these are nitrogens with R groups. So those are amines. We have an aromatic ring here and here. If you circled one individually and put alkene, that would be okay, but this is specifically an aromatic ring. And then that's not technically an alkyl halide, so I'm going to leave that one out, though I'm sure I would have accepted it on that test. All right, now notice the formatting's off here, so we're going to read this together. On the next page, we're going to have pairs of acids, and we're going to circle the stronger acid. And let's walk through that. So in the first one, if we draw the conjugate bases, we are going to have two carbons with a nitrogen with two lone pairs and a hydrogen and a minus charge versus a deprotonated amide, negative charge. So they both get a negative charge on nitrogen, so atom doesn't really help us here. But one of them does have resonance where the other does not. So this one is more stable, which makes it the weaker base, which makes this the stronger acid. In the next example, atom is what makes the difference. So if I were to draw the conjugate bases, I don't have room here. And I think these circles are supposed to be circling these two hydrogens. What I'm going to wind up with is either a negative charge on nitrogen or a negative charge on oxygen. Since oxygen is more electronegative and they're in the same row, that would hold the charge better, making this the stronger acid. And then in the last example, I have a little bit of room here. And I think the circles migrated down here. We would wind up with a negative charge on a sp2 hybridized carbon versus a negative charge on an sp hybridized carbon. This is more stable, so this is the weaker base, making this one the stronger acid. Now, number 4, we're just going to do the labeling and the arrow drawing and well, there's a whole bunch of stuff to do here. Let's get into it. We'll go one at a time. Add lone pairs. Well, a neutral oxygen has 2 lone pairs. A negative oxygen has 3. So we'll go in and we'll add those lone pairs, and I'm going to do my best to be very clear. Now, I'm also asked to draw the mechanistic arrow. So the acid is donating a proton to the base, but the arrow always starts at the electrons and goes where they are going. So that oxygen in the cyclohexane ring is giving electrons to the hydrogen to pick it up. Now, I should have made a more clear bond here so that I can show it breaking. I do my best to draw the bonds more explicitly. Now, an acid will have a conjugate base pair, and the base will have a conjugate acid pair. And you're okay if you put C acid and C base. I just don't have a lot of room here. Now, will the above equilibrium favor starting materials or products? Well, equilibrium favors the weak. So if I'm comparing my base and my conjugate base, which one of those is holding the charge better? This one is the weaker base because there is resonance stabilization. and my equilibrium will favor the weaker side. So it will favor the products. Now I'm just being asked generally, do I know what Lewis acids and bases are? So if a Bronsted-Lowry base accepts a proton, it is donating electrons. So what is happening here? It is the nitrogen that is donating electrons to the carbocation. So this would be my Lewis base, right? The one that is donating the electrons. Now the following problems are resonance. So we are going to draw additional resonance structures. I want you to remember on these, I'm not actually going to be grading arrows, but I will use them here to help explain. I will just be grading the structures. Formatting really doesn't like good notes, so we're going to do our best here and kind of blow this up a little bit. Okay, I have an allylic lone pair. I have also have pattern 4, but I'm going to go with the allylic lone pair. Push my allylic lone pair towards the double bond and then the pi electrons out. That is going to give me a resonance structure where both oxygens have double bonds and are neutral, and I have a lone pair on this carbon in the center. I've created a different allylic lone pair, so I'm just going to keep going with that pattern. And I also have a resonance structure where that negative charge is shared on the other oxygen. I think those are the two most significant resonance structures. When we have a cation here, we have two different patterns. I have an allylic carbocation, and I have lone pairs next to a cation. So I'm going to start with the allylic carbocation, and I'm going to move the electrons from the double bond to the single bond that has the carbon with the plus charge. I didn't touch the oxygen, so I'm going to leave that alone. And now I have a double bond here. Now, this carbon has 4 bonds. It still has 4 bonds. But this carbon, which had 4 bonds, now only has 3. So that's where my plus charge moves up to. Another pattern I could have shown, and I'm going to grab my eraser and get rid of this right here, is I could have also taken my lone pair and moved it towards the plus charge. That would give me the other resonance structure here. So I didn't touch that double bonded carbon. This carbon that had the plus charge now has 4 bonds. The oxygen, which had 2 lone pairs, now only has 1, and that's where my plus charge is going to be. These are going to be your 2 most significant resonance structures. And then finally, we're going to start with a neutral molecule. We don't have any allylic lone pairs. We don't have any allylic carbocations. We don't have any lone pairs next to plus charges. We don't have any aromatic rings, but we do have a double bond between 2 atoms of different electronegativities. So I'm not going to touch carbon-carbon double bonds, but carbon-oxygen double bonds I can certainly show resonance for. I leave these 2 alone. That carbon went from having 4 bonds to 3, so it has a plus charge. And the oxygen, which was neutral with 2 lone pairs, is now negative. Still overall neutral. Now that I have drawn this, I have other patterns to work with. I have an allylic carbocation to the right or to the left. So I could also draw this structure. Negative charge still on oxygen, this still intact. If I think about it, this carbon down here had 4 bonds. Now it only has 3, and that's where my plus charge wound up. I could have also gone to the other side. Now, 9, we're just comparing significance. So these are both valid Lewis structures. I'm going to draw in the lone pairs just to be just so I can see them. I'm also going to remind myself that this has one hydrogen, so it still only has one hydrogen. Now, the very first thing to look for when checking significance is octets. And when you have a positively charged carbon, you do not have a complete octet. This is going to be my most significant resonance structure because every atom have full octets, so full octets all around. If I am comparing these two structures, everything has a full octet. A negatively charged carbon has a full octet, so that first rule doesn't help us. The second rule is formal charges. Well, they each have a plus and a minus and a neutral atom, so that doesn't really help us. So we have to think about where the charge is located. The only difference is the negative charge is on the carbon or on the nitrogen. They both have plus on a nitrogen. So nitrogen is more electronegative, and so it is more more stable with more of that negative charge. So more stable with that negative charge. I think as we're rounding out towards the end here, we're going to do a little bit of nomenclature. You want to remember that you are looking for the longest continuous chain that has the most substituents. So I could go 1, 2, 3, 4, 5, 6, 7. Or I could go 1, 2, 3, 4, 5, 6, 7, 2, 3. Either way has 3 substituents. So whichever way I number it is fine. 1, 2, 3, 4, 5, 6, 7. I even could go 1, 2, 3, 4, 5, 6, 7. All 3 ways come out with 3 substituents. So it's going to wind up with the same name. So since this is how I numbered it last, let's just do this. It's symmetrical, so you'll find that whether you number from the bottom or the top, it's going to come out with a 3, 4, and 5. Now, I have 2 methyl groups, and then I have a complex substituent. This has a common name, so I can use its common name of sec-butyl. And so I could name this 4-sec-butyl. Excuse me, let's try that again. Butyl, 3,5-dimethyl. Butyl comes before methyl, and then heptane. Or I could use complex numbering. Remember, it's always going to number 1 at the carbon next to the parent, and then the longer chain. So in this case, I have a methyl propyl. Methyl propyl would come after dimethyl. So you could also have 3,5-dimethyl, 4, and then I'm going to open my parentheses so that I know the 1 is a secondary numbering, and it is a methyl on a propyl group, heptane. In B, we have a 5-membered ring. And whichever way we number it, we're going to get 1 and 3. So my longest chain will be that ring. And so I will use my alphabet here. I've got a fluorine, and then now I've got a complex substituent. Fluorine's actually going to wind up being first, and we'll talk about why. My secondary numbering scheme will be 1, 2, 3. So it's going to be a dimethyl propyl, and F comes before M. So when we're numbering this, it'll be 1 fluoro, 3, open parentheses, 1, 2, dimethyl propyl. We don't have a common name for that one. Cyclopentane. Here we've got a couple of bicyclic compounds. Our first one here has 2 bridgeheads, so 2 shared carbons. So this is a bicyclo compound. If I go to the left, I have 1, 2, 3 carbons. If I go to the right, I have 1, 2, 3 carbons. And if I go down, there are 0 carbons between the bridgeheads, and they should go in descending order. Then for the alkane name, I just count them all up. 1, 2, 3, 4, 5, 6, 7, 8. This is an octane. Our last problem is a bit bicyclic, but just shares 1 carbon. So this is a spiro compound. Do the same process to the right and to the left. Or to the left and to the right. To the right, I have 1, 2, 3, 4 carbons. To the left, I have 1, 2, 3. Remember, descending order. If I count them all up, I have 4, 5, 6, 7, 8. So this is also an octane. Oh, very last type of problem, I will most definitely give you some names where you then have to draw them. I recommend draw that parent first. Octane. 1, 2, 3, 4, 5, 6, 7, 8. And then just make it as easy as possible. You've got, let's see, a T-butyl group or tert butyl group on carbon 4. So if I count 1, 2, 3, 4, I can put a tert butyl group. And then on carbon 2, 3, 4, 5, 6, and 7, I have 2 fluorines. For B, I'm going to start with my parent, which is cyclohexane. And then on carbon 1, and it can be whichever carbon you decide, I have 2 bromines. And then 1, 2, 3, 4, 5, I have an isopropyl group, so I need to know what that is. And on carbon 1, 2, 3, I have a propyl group. Right, so just a straight chain. And lastly, I have decane. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On carbon 1, 2, 3, 4, 5, I have 1 methyl ethyl. So I know that means that's an ethyl group with a methyl on carbon 1. So also an isopropyl group. And then on carbon 2, 2, 4, and 6, I have methyls. And there you have it. That's just a quick walkthrough of exam 1. I hope that helped.